The next speaker will be Florencia Canelli from the University of Zurich. Latest results from the LHC, Higgs bosons and beyond.
No? Hello, good morning. I'll be talking about the latest result from the LHC, Higgs boson and beyond. As you probably know, this last year has been a spectacular year for particle physics, and if you are an experimental particle physics at me, this is probably the closer that it gets to feel like a rock star and being what people know what you do, and being in the front cover of most of the your results, being in the front cover of the most of the magazines around the world. So what I'm going to, so it will be silly of me to try to just not talk about this. I will talk mainly about the Higgs boson, the discovery of the Higgs boson, and what it means and how we got here. So the Higgs boson is said to complete the standard model physics of particle physics that is composed of quarks, leptons, and their interactions and their forces. The Higgs boson has been proposed in 1960s, and what I want to tell you now is essentially how we got to last year's discovery. For that, I want to take you on a journey to these 50 years of search. And it all starts in the 60s, where the Higgs mechanism is proposed. The Higgs mechanism is proposed and essentially tries to answer two questions. Why fundamental particles have mass, while the equations of the symmetries the equations essentially said that the particle should be massless they should be massless. Or another question, it could be why the weak force is so weak in comparison with electromagnetism. So answering that question, this gentleman came up with some theory where what they did is to propose a new scalar self-interacting field covering the whole universe with a non-zero vacuum expected value of 246 GeV. And in that way, the fact that it's non-zero value breaks electroweak symmetry breaking, and it generates three Goldstone bosons, that is the charge W and the Z boson, and one neutral Higgs boson, spin zero particles, and the fermions then, by interacting with this field, acquire mass. So that was an idea essentially to solve these theoretical, not satisfactory questions. By the 70s, if it existed, the only thing that we knew is that it would be between 10 and 1,000 GeV. So these are, in the 70s, there are not many theoretical papers on Higgs, but this is one of the, that predicts what are the masses, and this is one of the interesting ones because it says that actually, experimentally, we didn't have a clue where to look for. In the 80s, we start seriously with accelerators, and this is one of the first things that happens is that we have the discovery of the W boson at the SPPS. This is at CERN in the border of France and Switzerland, where LHC is now. And so this W boson is found to be about 80 GeV. Then LAB in the 80s starts taking data in 1989. And the first LAB, even though it is mainly proposed to study W's and C's, which it does for a whole decade, the first detailed Higgs study appears in 1986. And it does that, essentially studies W's and bosons for a decade and searches for Higgs for a decade. In the 90s, something else happens, that is The top quark is discovered at the Tevatron at 1.8 TeV proton-antiproton collision. This is at Fermilab. And what we find is that it has a huge mass. So this is the only fermion that significantly couples to Higgs. So now we have two tools. We have the W that couples to Higgs and the top that couples significantly to Higgs that can tell us something about the Higgs boson indirectly while we search for it directly. And this is what we do. This is probably one of the star plots in the last decade or more in particle physics conferences. This is the mass of the W, the measured mass of the W. This is the mass of the top. And what is yellow is the allowed region for the Higgs boson mass. That it goes, in this case, from 60 to 1,000 GeV. And what you find here is this ellipse here. That are the measured values of the W and the Z. And the measured values of the W and the top. So Higgs could be anywhere here. So essentially, measuring that indirectly constrains the Higgs. Now you can say here that we are not constraining that much, right? So and then beyond this white part was excluded by direct searches at that point. This is 1997. Well, by 2000, and this is exactly the year 2000, the lab ends in its run, and it doesn't find Higgs. And what it does is to create a very stringent limit below 100 at about 99% confidence level or something similar of that order. But it has limits, but it puts limits on 114 GeV. At that point, there's a modest indication of a possible signal in this range. But the lab stops taking data to allow construction for what comes next for CERN, that is LHC. In 2000, there are Tevatron upgrades to an energy of 196, and in that begins a decade of searches for Higgs and precision measurements of W and top. This is at the end of the 2000s. This is a plot that from 2010, from Summit Conference in 2010, where still the Tevatron was the only game in town on collider physics taking data at that point. And this is a plot of the direct searches. These are the limits on Higgs, where this part, where if it goes below 1 is excluded, if it goes up is about, this is the times standard model cross-section expected value. So at that point, what we have is that the Tevatron is able to constrain to have limits, and that's this white little region here. Everything else here is still allowed, but indirect constraints through the W mass and the top mass get very precise and indicate that the Higgs might be light in the lighter section and not so heavy as about 1,000 GeV. So by 2010, what we have in the 2010 in the decade, what we have is the Tevatron shuts down in 2011. So we are getting pretty close to where we are now. The Tevatron shuts down in 2011. We still have some precision measurements coming out. Maybe there's one more W mass coming out. But essentially, until now, we have the last top quark mass from the Tevatron, and as I'll show you later. And there is an evidence for Higgs-like particle coming from the Tevatron around 2012. Now, what happens is that LHC starts taking data at 7 TeV. It is a proton-proton collision in 2011 and 8 TeV in 2012. By winter 2012 and 11, this is what we have for these two plots. We have the W mass and top mass here again. These are the direct measurements of the top and the W, and all this yellow region here is what the LHC had excluded. So the only thing that we had not excluded in the low mass region was this little green area here. So what I'm going to do now, so this is story, so that we are at 2011, so what I'm going to do now is to tell you how, go more into detail into 2012 and tell you how the discovery was made and where we stand now on that. For that, I'll show you pictures of the LHC and remind you that right now it's not running, but the last run was at 8 eV, and it's a proton-proton collision. It has 4 detectors, and there are 2 multipurpose detectors. That's the only thing that I'm going to cover here, and it's CMS and Atlas. These are pictures of those. The Large Hadron Collider is a circular beam of protons and antiprotons that has 30 tons of, and it's huge. Large is probably an understatement here, and it's 30 tons of 8.4 dipole magnet. It's pretty cool. It's cooler than the outer space. The collisions are incredibly hot, 1 billion times hotter than the inside of the sun, and it's very empty. So there's to keep protons to bumping into things. So this is the last magnet, I believe, being inserted, the last or the first being inserted in the LHC, since it is a few meters underground. CMS and Atlas detectors are also huge. The Atlas is much lighter, but it's much larger. It's about half of the Notre Dame Cathedral. The CMS detector is much compact, as its name says. It stands for compact muon solenoid. It is much heavier, and the way that both essentially collect data is by using a tracker inside the detector, a tracker to measure the trajectories of particles, calorimeters to stop particles and measure the electromagnetic particles, and then muons and the muon on the side to help with reconstructing the trajectories of muons and measure their momentum. These are pictures of the CMS being installed in the cavern down underground. These are pictures of the Atlas being. These are the muon solenoid as you saw in the diagram. This is the cavern, and then here you can see how everything fits together, and this is the size of, this is a person here just for reference. As I said, the LHC took data from the first run from 2010 to 2012. It stopped taking proton data in December, and it collected an integrated luminosity of 28 inverse femtovars. So here this is with 8 TeV, and these are with 7 TeV. The peak instantaneous luminosity was 7.7 times 10 to the 34. And this creates a huge challenge in many ways, not just because of the amount of data that has to be collected and stored, but also one of the things that happens is that we have more than one collision per event. The experimental challenges for us are mainly to try to maintain a high efficiency on collecting data when all these pile of things are happening in the event. And so far, the LHC experiments have been able to do that very well, have been able to cope with that very well. Now, the physics processes at the LHC. This is the cross-section as a function of the center of mass energies of the collision. And what you can see here is that the most common things that are producing proton-proton collisions are jets. So everything that is produced by strong interaction goes high here. Then you have things produced via electroweak, much lower in cross-section. And here you have top, even though it's produced strongly, then the mass is very heavy, so it's produced more rarely. And here you have the Higgs. So essentially, to study Higgs, you need to understand all the things that happens here. To be able to get this event, you need to have a good understanding on all these physics processes. Beyond that is also there are good searches and also good standard model physics that is done with these processes. And here, to give you an idea of the rate, Higgs, rate in hertz, 0.1 with respect to bottom quarks of 10 to the 6, just to give you an idea of how challenging it is to get. So the most common things, so now I'm going to give you just a flavor of the standard model physics before we get to Higgs. So the most common things, as I said, are jets. So these are plots made with dijets, so which is the most common process that you have at LHC. So just speeding up 2 jets, and here is a reconstructed mass of those, the invariant mass of those 2 jets. So that's what we have here, and as a different rapidity in different rapidity beams. And what you can see here, red is the prediction, and black is the data. And you can see here that even over the orders of magnitudes, you have QCD predicting very well our data. And here, this is also another comparison. And there is a feedback here because the data also helps the next to leading order Monte Carlo, next to leading order calculation improves them. So for us, it's very good to have these things. And another thing that I want to point out is how high this is. This gets to an invariant mass of 2 TeV. The next thing is the Z cross section. So the electroweak just producing Z's, that is also a pretty common type of event. And what you see here is the cross section as a function of the center of mass energy. Here is what we have from Atlas and CMS. This is taken in 2010, and you can see how well we've been doing. This is the fit, and this is what we have found when in UA1 and UA2, and then this is the C cross section from the Tevatron run 1 and run 2, and then this is what we have now. So it's a good agreement. Another thing was that you have, if you can scan just 2 muons, the invariant mass of 2 muons, and find and reproduce decades of physics that were things that were discovered decades ago in a very short period of time at the LHC. So here we have an eta, all the mesons, eta mesons, and here the Z boson. I put the dates of their discoveries, and if we had enough data, we could see here in this plot. This is only for inverse picovar. Here you could see also the Higgs just doing this plot, but it's very hard to see it in this channel, as I'll tell you later. Now the next thing in cross section, going lower in cross section and making rare processes, are die bosons. So these are again. This is the Z cross section that I just showed you, and here what we have are the production of 2 bosons together. These are not only just backgrounds for many of our searches in Higgs and beyond the standard model Higgs, but also have a good program of physics by looking for triple gauge couplings and physics beyond the standard model. So in here we also find a good agreement. There's a similar plot for Atlas, and there's a very good agreement between the cross sections of these processes and the prediction. The other thing that I want to point out is that these processes were just observed at the Tevatron a few years ago, and now these are very well measured here. Okay, now the other thing that, as I said, there's this connection and this indirect connection between Higgs and W and top. So measuring the top mass, the W mass and the top mass, it has been a very important output of particle physics. So here, in the last year, one of the things that happened is that the CDF made the last measurement of their W mass. The 0, I believe, is measurement will come later. And here, what we have is a precision. Here we have a world average for the W mass that it has an incredibly precision. And the point that I want you to take with this is that this is in a proton-antiproton collider. So it's in a hadron collider where things are pretty messy, and we are still able to, after a lot of years and work being able to extract a very precise number. Similar for the top quark mass, the top quark mass has reached also an incredibly precision. It's about, the Tevatron's last number is about 1 GeV of precision of a mass of 133. And the CMS now, the LHC is now measuring this is the top quark mass too, and is reaching similar precision than the Tevatron. So the only thing here is that beyond that precision, there are things that have to be said. And I think that right now we are, till those systematics till we don't learn more about those systematics, it will be harder to reach beyond this uncertainty. The reason is because the interpretation of the top quark mass is difficult. At this point, we know that we measure the pole mass here, but it is now, since the top is unstable and colored, it might be that we need the connection between the pole mass and the MS bar. So this is something that LHC is currently working on trying to understand that further. So now going to the Higgs boson, in July 4th last year, there was an announcement of a Higgs-like particle. And for that, I want to get a little bit into details on how the particle is produced, decayed, and detected. So Higgs bosons at the LHC are produced mainly by these 4 processes here, where the most common is gluon fusion, which is this one. So as you can see, and I'll point out later, then there is the Higgs couples here with a top, or in these 2 cases with a W, and in this case to top again. So those are the diagrams. Then it decays, and it decays with these branching ratios. The standard model predicts predicts these numbers, and it says how much fraction of which is going to decay to. So here the most common is fermions, but the discoveries are made by the ZZ and the gamma gamma, these little tiny ones. And the reason is because they have less background. And here what we have is actually the data and the prediction as we keep taking. So you can keep seeing that as we take more data, these numbers, you will see a peak appearing here. This is the Z, and this is the di boson. As I mentioned before, this is the ZZ di boson, and the same thing for CMS and for Atlas. And here you see the second peak, and here you can see this is the signal appearing here. This is about more than 6 sigma. More than 6 sigma, and that data was all the 2011 and 2012 data. The Higgs to gamma gamma is a similar story. Now in Atlas observes a 7.4 sigma, and this is a down fluctuation, this is a high fluctuation, observes a 3.2 sigma right now. Again, this is the case to 2 photons, so what you do is to reconstruct the invariant mass of the 2 photons. A new thing that happened a month ago or so was the evidence in this channel in WW, where in this case we have the W decays to leptons and neutrinos. So it's a pretty unconstrained final state, and then this is the transverse mass of the event, and the red is the signal. And the level that we have there now is about as an evidence of the decays to boson. So the question is it the standard model Higgs boson, or is it a Higgs boson? And for that, we have to ask the right questions. And the first one is, does it couple to bosons? I think I convinced you that it does couple to bosons in the last few ones. Does it couple to fermions? And that's something that we need to know. And are the observed rates in each channel compatible with the standard model prediction? If the new boson also has certain properties, it should be a spin 0 and CP even, it has CP even coupling. So that is something that we need to measure. And in the last 6 months, I believe that we're attacked all those questions very aggressively. The couples to fermions, I think the best way to convince you that the couples to fermions is with a plot from the Tevatron. Here you can see that the Tevatron sees more than 2 sigma, 3 sigma level for evidence for that it decays. In the case of that it decays to Bs. In the case of the Tevatron, the main analysis is Higgs to B bar. So that's something that, and it's expected sensitivity expected with the LHC, with the full data of the LHC, but they have not finished that analysis yet. But okay, so you know, in the case of two big quarks. It also, Atlas finds, so the CMS finds that, oh, I think I put it wrong. CMS finds a 3 sigma, about 3 sigma, short of 3 sigma, that it decays to taus. And Atlas, I just want to show you that it is very an insensitive analysis right now, but it's very promising that we are looking at the lowest, one of the lowest branching ratios, that is Higgs to mu mu. So we are attacking that too. And as I said, now we have to compare how consistent those rates are with the standard model. And here, this is a plot of the signal strength for CMS, and this is for Atlas. And both of them are consistent with 1, meaning that it's consistent with the standard model, and they are consistent with each other. So combining this is probably giving you something that is really similar to really close to 1. In Higgs to gamma gamma and Higgs to ZZ, we measure the mass of this Higgs boson. Atlas has combined these two, and this is the number, and then these are the numbers for CMS and Atlas for Higgs to ZZ and Higgs to gamma gamma. The number to take home is that it's probably about 125 GeV plus minus 0.3 GeV. The production modes, as I said, they are produced by interacting with tops and with Ws. And one of the things that we do is to group together the ones that are coupled to bosons and the ones that are coupled to fermions. So, and here we see the standard model will say that the number will be 1 and 1 here. So this is the black point here, and this is what we found here. So right now it is pretty, this is a pretty insensitive plot. The uncertainties are very large, but it does seem like it is consistent with the standard model so far. The next thing is to look if it couples to fermions and vectors, and as the standard model predicts. And these are plots of, now it's similar grouping to what we did before, but also taking into account the decay. Where here we have the couplings to fermions, and these are the couplings to bosons. Same thing, this is for Atlas, and this is for CMS, and this is for Atlas. It is degenerate since you have here a square. You have a square, but this plot is just constrained and constrained to the positive section. But actually, this is what we see. And again, what we found, this is the standard model here. This cross here and this point here, and we find that all the channels seem to be consistent, although, as again, there's data needed. The spin and parity studies, one of the things that we did was to check how consistent the data is with the standard model by also seeing how inconsistent it is with other models. And we have tested many models of JP, many different JP models where they are different than 0 plus. And what we find is that most likely it is consistent with the standard model, that is a 0 plus value. That is true for both experiments. So how self-consistent is all this with the standard model? So here we have again the W, now more fancy, W and top mass measurement. So here this blob here is what if you only knew the Higgs and you didn't know the W and the top, what it will say. Well, it says that this is the W mass should be around here and the top mass should be around here. And the green and the yellow one here says these are the experimental values of W and top. So it is pretty consistent right now. So what we have found, the Higgs that we have found with what it was predicted by this plot. And it is an impressive consistency. But we will benefit if there is we will benefit from more precision on W top and even on the Higgs much more. So again, so is it the Higgs boson, a Higgs boson, or is I think the decay rate, spins, and all that is consistent with the standard model, but data, the statistics are low. We need more data. And wow, okay. So since March now, we don't call it a Higgs-like particle. We call it a Higgs particle. But it's because non-standard model Higgs can have similar properties, and this is something that we we have to investigate. It is a Higgs boson, but it might not be the Higgs boson of the standard model. Which brings me to the last part of the question, and it's the implications of 125 GeV Higgs boson. I'm not going to go into more detail here because I think that it will get into the theory section more than experimental, but what I want to say is that what we know, the fact that it's a 125 GeV Higgs boson, means that our theory of the standard model is fine-tuned, meaning that we need huge corrections to cancel out to give us a Higgs boson of 125 GeV. That we find it unnatural, and we again find it theoretically unsatisfactory. And we have, found this for a while since it was predicted that the Higgs boson was going to be high. So there might be a physical principle that keeps Higgs light, and that is something that we want to do, that we want to know what it is. SUSY, supersymmetry, is one of the most popular solutions to this because it introduced SUSY loops that cancel these loops naturally, and then cancel these loops naturally. So the only thing is that it gives you more Higgs. One of these Higgses is very similar to the Higgs of the standard model that we just found. So the question is, can we find these other Higgses that SUSY predicts? The other thing is that the biggest contribution to these top loops, to cancel these top loops, is the stop quarks, and that is also something that we want to see if we can find, or if it is, see if we can find. So what we know is that these particles, it cannot be that heavy if they are going to cancel this loop. And now I'm going to go even faster. Okay? So there's this charge Higgs that is part of the SUSY. We search for that. This is a diagram of this. This is mainly coupled to taus and to Bs. And this is one of the searches that we do. What is in white here is the allowed region, the still allowed region. So there's still room for this particle to exist. CMS results are comparable. Then there's also a prediction for the neutral Higgs, and these are the limits. These are also, again, very stringent limits where, below 200 GeV is getting pretty hard for this neutral particle to exist. And then this is a summary plot that has many channels. This is from Atlas. It's a summary plot that has many channels on direct production of stop quarks. And what we find here is that the limits on this particle is about 600 GeV, and that's a question mark. Is it getting too high to be to still be SUSY the solution to this fine-tuned problem? So. And that's still a question mark. It's not. I don't have the answer. So now beyond Higgs, we still, and beyond looking for what theory says, we also look with eyes open to all the data. We looked for resonances. In this case, this is a resonance search using digits. This is the most stringent, probably, search. The one that reaches the highest energy for sure. Highest energy is here. You have 5,000 GeV, and we look for in many signatures. We do signature based, and then later we add models to see what is it that we expand, what is it that we excluded. In this case, this is the CMS plot, and this is the Atlas plot for just looking for bump in invariant mass of two jets. There's an excellent agreement, and there's no bump, unfortunately. There are more resonance searches and more resonance searches. In this case, for instance, these are the diboson. These are the diboson channels, and these are diboson channels, and also C primes and W primes. There are a lot of searches done by CMS and by Atlas. This is a summary of them and the limits that they set. Now, I want to take 2 minutes to talk about the future. And right now, as I said, we are not, the LHC is not running right now. It's in a long shutdown. And it's done to go to the design luminosity that is 13 TeV. After that, in 2015, more or less, up to 2018, it will be running at 14 TeV. After that, there is another shutdown, and it will be running after this shutdown 2 again at 14 TeV, but with higher instantaneous luminosity. This is what it happens. After that, there's a long shutdown 3, and here the idea is not to change the energy, but then actually change to go to even higher luminosity, and that is called the high luminosity LHC phase. Now projections. So as I said, so one thing to take here is that here we are going to collect it's expected to collect 300 inverse femtovars, and here 3,000 inverse femtovars. So the question is, what does 300 inverse femtovars look for Higgs and 3,000 inverse femtovars? So here we have a projections, and these are the projections on those couplings that I showed you before. And these are the percentage in systematic for these couplings. And you can see that with 300 inverse femtovars, if we don't do anything, that means that if the uncertainties stay, if we don't work on the uncertainties, somehow they stay similar, we have now, we are going to be between 6 and 15% uncertain in these couplings. If they are scaled here, then we can get to 5 to 9%. Then 3,000 inverse femtovar, actually we can get, if things go well, between 1 and 3%. So that's something that we will profit from more statistics, is to be able to understand this Higgs sector much, much better. You can ask, is that good enough? Okay, that's the question. So now, far beyond the LHC, these are 2 tables. I have 2 more things. So these are 2 tables that went to it's a proposed update to the European Strategy for Particle Physics, where you can see these are the two upgrades that I talked about just now, and then there's other ideas on the table. This is the high energy LHC. This is a center of mass energy of 26 to 30, and then there's a very high energy LHC, where it's 42 to 100. These require not only changing the tunnel to be 80 kilometers, but also this one requires changing the magnets. And then the other option that is also on the table is to talk about lepton colliders. In this case, we are more familiar with this, but then there's also this T-lep, which is essentially the same ring that this one will use, but instead collide leptons. This is just to give you a sense of scale. This is the LHC now. This will be 80 kilometers. There's people studying how to make this tunnel through the Jura Mountains. And again, these are just to give you an idea of scale, the different linear collider options that people are talking about. Okay, so to conclude, about 50 years of experimental searches for the Higgs boson just concluded successfully. We are very happy about that, and Higgs boson is compatible with the standard model so far, but it opens a new program of measurements. The first LHC run has ended. It has explored many aspects of the standard model, and it has also pushed the physics beyond the standard model closer to the TeV scale. Now the LHC and experiments are going upgrades, and we'll start collecting data at 14 TeV in 2015. So there's good prospect for more measurements, more precision measurements, and hopefully discovery for new particles. Thank you.
Florencia has asked that we defer the questions until after Tim Tate's talk, because Tim is talking about related ideas.